Hello, this is Prof. Nanius, and what we want to do today is I want to give you a video that will show some of the linear algebra that we have not been covering in class. Um, and I'll just go ahead and start with a very brief example. So let's go ahead and share that screen and get started and get rid of this. Okay, so link to linear algebra. Now suppose and I'll start this problem like we're doing in class. So suppose we have the following differential equation, system of differential equations. We had this case, let's say x prime, y prime equal the following matrix, 1, 2, -1, and 4, times, let's say xy, where x and y are functions of t, and let's say x of 0 is 1, and y of 0 is, let's say, 2. Now, how we've been doing this in class? In class, what we've been doing is we've been doing the Laplace transform of both sides. So we'll take the Laplace transform of this. And we're going to go ahead and remember these are constants. And I'm sweeping a few things under the rug, but these are the functions here. And what I get out of this is this vector equation, the Laplace transform of a function x prime is sx minus x 0. So in this case, what we'd have is we'd have sx, we'd have sy here, minus, in this case, 1, minus, in this case, 2. And we would have this equation here. And this would now be x of s, y of s, instead of t. And so what we've been doing in class is we now can write this in vector form, minus the vector 1, 2. And writing this down, we have, this is big X, I'm suppressing the s here, plus 2y, and that's minus x plus 4y. And then doing a little bit of matrix algebra, we get the following matrix equation, or vector equation, actually. This is still a matrix here, so let's not quite be that sloppy. Well, actually, this is correct, but now let's just do, this is going to be x minus sx plus 2y and minus x, and this would be 4 minus sy. And then the way we solve this in class is we use matrices. So I probably shouldn't have gone back from the matrix again, but here we go. And look at what we have right here. This is 1 minus s, 2 minus 1, 4 minus s, times x, y. These are capital O. This is x of s, that's y sub s. So we have this matrix equation now. And what we said in class is now we took the inverse matrix here. And in class, we taught you how to do the matrix inverse by the adjoint method, where we flip these diagonals and multiply the off diagonal by negative. And then we also had to divide by the determinant. So it's 1 minus s, 4 minus s, minus a minus 2. And that is going to be the Laplace transform of your solution. And so let's, what I really want to do is I want to focus on this right here. It's going to be important, this thing. We'll see this again. And then let's finish up the solution here again. So this is 4 plus 2 is 6, minus 4s minus 5s, okay, and plus s squared. And when we do this multiplication to turn it into a vector, we get s minus 4, and then we minus 2 times the minus 2 is plus 4. And again, multiplying this, I get a negative 1 plus 2s minus 2. Now, this bottom thing here, this factors very nicely. This factors as s minus 3, s minus 2. And let's just do a little simplification. That's an s. This is 2s minus 3. I should not have drawn that little. It's not a fraction. I just got carried away. That is 2s minus 3. And then we would end up getting the solution in terms of the Laplace transform. We know that x of s is going to be s over s minus 3, s minus 2. Or y sub s would be 2s minus 3 over s minus 3, s minus 2. Now we could, if we wanted to, well, we now need to do partial fractions to get this. So let's just finish the problem up. And I will get to the main point of this video in just a second here. This one here, if I do the partial fractions, it's expansion. That's going to be a over s minus 3 plus b over s minus 2. So s, clearing the denominator, by getting a common denominator, we multiply that by s minus 2. I'm skipping a few steps here because my class have seen this. So in this case, let's see here. Let's try s equal 2. We get 2 is equal to minus b. So b is negative 2. We try s equals 3. We get 3 is equal to a. So your x of s is 3 over s minus 3 plus minus 2 over s minus 2. So x of t is 3 e to the 3t minus 2 e to the 2t. And then let's do the y now. Let's do that in red. Well, here we are doing the same clearing of the denominator and using the a and b as before. Same verse, same as the first. Using s equals 2, we get 4 minus 3 is equal to negative b. So b is negative 1. Using s equals 3. Give ourselves a little room here. Using s equals 3. We get 2 times 3 is 6. 6 minus 3 is 3. So a is 3. So your y sub s is 3 over s minus 3 minus 1 over s minus 2. And then we get the solution for y. 3 e to the 3t minus e to the 2t. So we've solved the problem that we set out to solve. Okay? Now, notice we really have, other than finding a matrix inverse here that we did by the adjoint method, used very little linear algebra. And if you read the text will tell you, the text will say that 3 and 2 are eigenvalues of the original matrix 1, 2, minus 1, 4. So that's what they will say, eigenvalues. Now, where does that all come from? So let's look at what we just did. Now look at it from the linear algebra point of view. So using some linear algebra, which we did not develop in class, and this is a general idea. You start with this vector xt, which the derivative of which I'll write like this. And that's going to be equal this matrix A, which I'll do A, B, C, D, times functions x of t and y of t. Now, just like we did when we did differential equations with linear differential equations with constant coefficients, what we do is we seek a solution where xy will be some constant, let's say v1, v2, times e to the lambda t. Now, you might be offended by that, saying, why are we seeking that kind of solution? Well, remember, there's such things as existence theorems and uniqueness theorems. And what they mean is that if you find a solution by hook or crook, and you can prove it's a solution, then the uniqueness theorems, again, we didn't cover those, will tell you that you found them all. So that's what enables you to try stuff in differential equations. So if this is the kind of solution we're looking for, then if I take the derivative vector, what I get is the derivative of e to the lambda t is still lambda v1, v2, e to the lambda t. So if we go back to our original equation, this one here, what we really are saying is we're saying this is a derivative vector, so we'll have lambda v1, v2, e to the lambda t is equal to this matrix times this. Remember, this vector is this. This is going to look a lot like what we did, I forget the chapter, but we did the constant coefficients. Now, we use the fact that e to the lambda t is never 0, not even for any complex number. So we divide both sides by that. You can do that. What we have is we have the algebraic equation, lambda times this vector is equal to this matrix times the same vector. Now, so in other words, this vector times this matrix is a multiple of itself. And if this happens, what we say is we say that the vector v1, v2 is an eigenvector, that means self, for A, B, C, D. In other words, matrix multiplication takes it to a multiple of itself, and the lambda is the eigenvalue for the matrix. It's an eigenvalue. Okay, so that's where the terminology comes from. Now we're going to do even more with this, and just hang in there. We're going to do a little bit more with this, and you will see something very familiar. So that task is to find this and this. And this is how it goes. If this is true, then we have the 0 vector, which I'll call 0, is equal to this matrix times this this column vector minus lambda times this column vector. Now this makes sense because this is a 2-row by 1 column. That's a 2-row by 1 column, so you can do that. However, I'd like to make these into something that I can combine. So what I will do is I will do the following linear algebra trick. And this is a technique. What I can do is I can insert the identity matrix here, and that will not change anything. But what it enables us to do is we can now factor out the V1, V2 and not get nonsense. If I tried to factor this out here, I'd have a 2 by 2 minus a scalar, which is nonsense. Here, though, if I try to factor this out, this is really A, B, C, D, V1, V2 minus lambda on the diagonal, V1, V2, like so. It's minus here. This is not equal. This is a minus. So that does make sense. So what I now have is a 0 vector is equal to, look, you're just taking this along the diagonal. And you're solving here. Now, that's the first thing. Now, I want you to take a look at this matrix, this one right here, and compare it to this one. The difference between this matrix and this matrix is here. We've replaced lambda by S. That's it. That's really it. And a fact from linear algebra, linear algebra fact is that this matrix here, this matrix M has a non-zero eigenvector. I should say the matrix A, if and only if you take the matrix A minus lambda, B, C, D minus lambda, has determinant 0. In other words, it's singular. So what we do here, that the determinant is going to be A minus lambda, D minus lambda, minus B, C, and this is just the characteristic polynomial with lambda in place of S. So the roots of the characteristic polynomial are in fact the eigenvalues. So if we go to our original matrix right here, which is 1, 2, minus 4, and we just took the determinant in this case, that's going to be a 1 minus lambda, 2 minus 1, and that's going to be 4 minus lambda. What we get is 1 minus lambda, 4 minus lambda, plus 2. And what we see, this is lambda squared, minus 5 lambda, plus 6, which factors into lambda minus 3, lambda minus 2. And notice, compare that to S minus 3, S minus 2. So we see here the eigenvalues are real and distinct. And that is how we when we do Laplace transforms, that's kind of what we're doing. Now, if you wanted to finish this problem without Laplace transforms, this is not how I'm teaching it in class, but in case you're curious, what you do right here is you'd use one of the, let's say this use lambda is 3. What we now have is 1 minus 3, 2, negative 1, 4 minus 3. That's going to be minus 2, 2, minus 1, and let's see here, and 1. And we want a vector, v1, v2, that if we multiply it by this, we will get the 0 vector. And that's pretty clear, v1, v2. You can just do a little bit of algebra here, but basically it's just 1, 1. This corresponds to lambda equals 3, so one solution is the vector 1, 1, e to the 3t, and that's the x and that's y. If you go to the solution that we obtained right here and write it up and down, there we go. We have 3e to the 3 y, 3e to the 3t. So that works as well. So that's one solution. And what we do is we multiply this by an arbitrary constant because I haven't used initial conditions. Now if we use lambda equal 2, what I get is 1 minus 2, 2, negative 1, 4 minus 2. That's going to be negative 1, 2, negative 1, 2. And a vector that works, that gives us a 0 here, if I do the vector 2, 1, that works. So the second solution would be C2, 2, 1, e to the 2t. The x coefficient is twice as big as the y coefficient. And if we go back to our solution here, the x coefficient for e to the 2t is twice as big as a y. So we get so basically we got the right solution. We just had initial conditions there. So the solution we obtained, and I should point it out here, the solution we obtained at first, here we had 3's for that case. So here, so for our problem, C1 is 3. And then the second one, right here, is C2 is negative 1. That's what we did with Laplace transforms. So you see, you get the same thing. What changes is that you do have to do the eigenvector calculation that we don't have to do with Laplace transforms. But the roots of this polynomial, the characteristic polynomial, are in fact the eigenvalues. So that's sort of the connection that we're missing in class, but we did not have the time to develop the linear algebra to do this with eigenvectors and eigenvalues. But that's sort of a rough and dirty of the similarities there. And it really is the same kind of technique. Just the algebra is a little different. So thanks for watching.